Okay, so the last video we left off with this question. These are the parameters for some track and field event. This is how long it takes the athletes on average to finish the event. And of course, we have some standard deviation, some variability in that. What we want to do is identify what running time would define the fastest 15% of these college students so that they get an invitation from the United States Olympic Committee to try out for the Olympics. Okay? In reality, they would probably use a cutoff that was smaller than 15%, but that's what we're going to do. Okay? So let's draw the curve to help us answer this question, and we'll assume normal distribution of the scores. So here we go, and here are the running times with an average of 57.37 and standard deviation, let's fix that there, a standard deviation of 6.11 seconds. I'm also a little bit, I think if we had these actual data, the standard deviation would probably be far less than 6 seconds because running speeds tend to be quite consistent, okay? Maybe not this much variability. Certainly at the Olympic level, and I'm always amazed when I see like the luge times that, you know, they're within hundredths of a second of each other, but we'll just use this for the sake of argument and to get this problem solved. So we want to identify the fastest 15%. Now, if you did this homework, a number of you were tricked. Now, I always tell students, and when you get to be in a professional position, there's no such thing as a trick question, but people can get tricked. I mean, all the information is here. If we're talking about running time, like this, how long it takes you to get around the track, where are the fastest 15% of the people? Some of you put those 15% up here, but of course, these are people that have running times larger than 57 seconds. That would mean that they're slow, okay? And as soon as I say that, people are like, oh, of course, of course. So I use this example, not to trick people, but to show you that you can be tricked, of course, because the fastest people are down here. That is, their times are lower. The fastest people have times that are less than 57 seconds, okay? So we're really talking about this group of athletes that have smaller running times, right? Under 57 seconds. So here's the fastest 15%. Of course, we're going to turn that into a proportion so that I can use my z-score. This would be their time. This would be their z-score, which we're going to get from the table. Okay? So 15%, the fastest 15% is given by this portion of the curve. I'm going to get my handy dandy textbook out here so I can use the unit normal table. And I want 15% in the tail, right? 15% in the tail, 15% in the tail. And here I go, 15. So I'm going to use, the closest is 14.92. Again, if you look at the table, you can see that our 15% exactly, our 15% falls in between two values. If somebody was going to be really picky about it, and if I were on the United States Olympic Committee, I would be picky about it because we're talking about tens of thousands of student athletes. But for our purposes, let's use a z-score of 1.04. Everybody with me? And in fact, this would be a negative 1.04 because it's below the mean. So now I have my three variables. I have negative 1.04. I'm looking for an x value. That is, what running speed do I have to make to get a letter of invitation? The mean is 57.37. The standard deviation is 6.11. And so let's do the calculations here. 6.11 times 1.04 equals, 6.11 times 1.04 equals, that's negative 6.35. Negative 6.35 is equal to x minus 57.37. So I'm going to add 57 to each side. 51.02. Okay. 51.02 is my answer. That is any running speed 51.02 or smaller, right? Because if you're running faster than that, you'll certainly get a letter of invitation. And so in this case, we're going to use our unit normal table, our z-scores, the parameters that we have, and we have our answer. Okay? So anybody that, if I had my spreadsheet with my 10,000 athletes on it, all I do is search for numbers that are this small or smaller. Okay? Now, if you did the computations the other way, you would get an answer something like 63.5, a little bit higher than that, 63.5 seconds. Once you got that answer, and I encourage you to do this always in this class, once you get your answer, I would encourage you to look at it and say, does that make sense? Does that answer the question in a way that makes sense? If people are taking more time to run around the track than they certainly are not than average, they certainly aren't going to get an invitation. Okay? So, if you got tricked by this question, I don't feel badly about that, because when you make a mistake like that, it's very memorial, right? You're not going to forget it. And so you're like, oh, keep track of, make sure that when I said fastest, that means that people have a low running speed. Okay? All right. Okay, so let's do maybe one or two more examples, and then we can move on from there. Okay, but this is very powerful. This is going to be setting us up for making that transition into inferential statistics. So I have a story to share. I won't share names, but I do have a story to tell, and that is a very good friend of mine from graduate school years ago. I mean, this is now 20 years ago, I suppose. He and his wife had a baby, and so I went to see him and the new baby, and I looked at the baby, and I was a little bit sort of surprised to see that this baby had such a big head. Now, the baby looked like it had a big head. I didn't say anything, but after a little while, my friend said, "Hey, my baby's got a big head, doesn't he?" And I'm like, "Oh my God, yeah, it looks like a big head. It's like a gigantic head, like a melon head." And he's like, "All right, settle down." No, I didn't. I wasn't that insensitive. But when we talk about, when you have children, or if you have children, one of the things that new parents do is, pay very close attention to how their children is behaving, how the children is growing. Is this normal? Is that normal? Does my baby have a big head? Should the baby be talking now? Or so on and so forth. And we know that there's lots of variability in all sorts of growth patterns and all sorts of characteristics of babies. And so the question is, how does my baby compare to normal? And getting back to this example with my friend, it could have gone in a weird direction. I could have said, hey, your kid's got a big head. And my friend might have said, my kid doesn't have a big head. My kid is perfect. It's just a perfect little baby. I'm like, well, it's a big head. And he could have said, no, it's not a big head. Now, notice what's happening here is, this really does not come down to opinion. And if the parents were concerned that the baby had a big head, they might go to the doctor and ask her, hey, do I have something to worry about here? I mean, there's something called hydrocephaly, right? Where a child might have a bigger brain than normal and something might need to be done with it. Or we could talk about microcephaly, where the child might be developing abnormally and have a small head. The point here is there are data to speak to this issue. And in fact, if you go to a pediatrician, she will look up those data. She will do the measurements on your baby and look up the data and see if there might be reason to be concerned. And this is all based on z-scores and percentiles. So I bring this example up because sometimes people think that this is just irrelevant to their life. And I'm like, I don't really think so, you guys. You should think a little bit more carefully about what we're talking about here, okay? So let's use this example. And in fact, I did Google this information, and what I found was, if we look at baby head circumference, okay? Baby head circumference. What we find is, and this is baby heads at about 1.5 months of age, that the average circumference for a baby head is about 38 centimeters, okay? And the standard deviation is about 1.5, okay, centimeters. So that if you have a baby that's 1.5 months old and the baby's head is 38 centimeters in diameter, in circumference, I should say, then your baby is average, right? And sometimes people will say, will kind of use the term normal. I mean, they're average, so they're normal. But we know that baby heads vary by about this much. And so let's say that my friend's baby's head is, let's say 41.27 centimeters. Okay. Well, what does that mean? Well, we certainly know that the baby's head is larger than normal, larger than average. Okay. But the question is, how much larger than average, right? Well, we can get the deviation score, but we can also put that in terms of a z-score. So here we are out here at 41.27 centimeters, okay? Let's get the z-score for that size head. Well, that's pretty straightforward for us now. You guys are getting the hang of this, right? And so you're being more sophisticated than just saying, he's got a big head. It's bigger than average. So let's do this. 41.27 minus the average of 38 divided by standard deviation of 1.5. And so the z-score here, let's get my handy dandy, 41.27 minus 38 divided by 1.5. Okay, so the z-score is 2.18, which means that this baby's head is more than 2 standard deviations away from the mean. And of course, I hope that you remember from a couple of videos ago that that's pretty far out there, okay? We're at 2.18. But now what we're going to do is we're going to figure out what the percentile is. That's often what's used for developmental landmarks for children, is what percentile are they at, okay? And so I'm going to look up my z-score of 2.18, okay, right here. And in the tail, 1.46%. In the body, right here, 98.54%. And so in terms of percentiles, here's where the baby is. 98.54% of the population of 1.5-month-olds, 98.54 are at or below. So there's only less than 1.5% of babies that have a larger head than what this baby has. This is no longer my opinion or my friend's opinion, I mean, because we both agree the kid has a large head, right? This is no longer our opinion. And if we went to the doctor probably wouldn't say, wow, your kid's got a big head. The doctor would say, well, let's take a measurement and we will then see what the percentile is. It gives us much more information about where this baby is. And so, in this case, it might be prudent to do a follow-up test, maybe do a CAT scan, and see, you know, does the baby have some problem, you know, with hydrocephaly or a tumor or, you know, something like that. And in fact, the baby was normal, and that baby is now in college and doing quite well. There was no problem. I think this baby had a huge, good brain. Very smart kid. Very smart kid. But this is how it's done. This is not just for stats class anymore, right? I mean, this is how physicians make judgments about a whole number of things. I mean, any kind of blood test that a physician will conduct for you, they will look at what is the average level of whatever they're measuring. They'll take this into consideration, and you typically will get a percentile. This is how it works, folks. This is how it works. And we're going to be using the same kind of strategy when we make decisions about research findings, okay? So whether it's height or level of, you know, protease in your blood, I don't know, just making it up, or whether it's running speed, or whether it's IQ, or whether it's how far you can jump, or whether it's the temperature today, you know, is this beyond the average temperature or not based on the standard deviation. All of these things, medical professionals, ESPN decision makers, awards conference, research scientists, educators, you know, whatever it is, psychologists, they're measuring these things, and this is exactly what they use. Z-scores will allow us to get percentiles. It'll tell us the position in the curve relative to the average and the average deviation. Okay? This is how it works. Okay. So let's do another example. And in this case, what I'm going to do is let's do a psychology example. Let's suppose that I'm interested in reaction time. I'm interested in reaction time in humans, and what I'm going to do is, and you know, other things that might affect reaction time, whether it's drugs or concentration or the stimuli that I present or something like that. So what I'm going to do is I'm going to set up my subjects, they come in to my lab, sit at a computer, and I flash letters on the screen, okay? And I tell them, as soon as you see the letter X, I want you to hit the space bar as fast as you can, and then the computer keeps track of the reaction time. So then that is the time between when I flash the X and when the person hits the space bar. Okay? So we're going to measure reaction time. And let's suppose that the average reaction time for people to do that is 258 milliseconds. Okay? That's about a quarter of a second, because 1,000 milliseconds make up 1 second. Okay? So let's say that on average, people take about 258 milliseconds to do this task. Of course, not everybody does it at 258 milliseconds, right? And so we want to describe where's the average, where's the central tendency of this normal curve. We're going to assume normality. And then we want to indicate what kind of variability around that average would be. Okay, so let's say that the standard deviation is 37 milliseconds. So on average, they respond in 258 milliseconds. There's a bit of variability there. Some people are faster, some people are slower, so on and so forth. Okay. So here's what the distribution would look like. Okay, here's what the distribution would look like with a mean of 258 and standard deviation of 37. Did I say 37? Okay. Once again, most people are, because this is in a normal distribution, the mean is also the mode. So most people are around 258, right? And of course, this is also the median. So about half the people would be below, half the people would be above. And of course, we have to count the people that actually would be 258. But this is what the distribution would look like, okay? So, person comes in the lab, student comes in the lab. Let's call the student Bob, okay? And Bob sits down at the computer, and I give the instructions, and I say, okay, when you see the X, hit the space bar as quickly as you can. And Bob, so I need to do a little bit of back calculation here. Bob's score, just do this as Bob. Bob gets a reaction time of 338 milliseconds. 338 milliseconds. Here's the question I have for you. And in fact, once I ask the question, maybe I'll say pause, because I want you to sort of think about your answer, give your best guess, okay? So here's my question. Do you think that Bob is intoxicated? Okay, so you can pause. If you want to do some calculations, you can pause. All right. So the question is, do you think Bob is intoxicated? Now, the question was not, is Bob intoxicated, right? The answer to the question, is Bob intoxicated, is, how the hell do I know? Okay? What I asked was, and you can replay the video, I asked, do you think that Bob is intoxicated? And of course, the inappropriate response is, I don't know, because that would tell me that you're not thinking, okay? Based on these data, do you think that Bob is intoxicated? or not, right? Because those are the two options. Is Bob intoxicated or not? Now, what I'm getting at here is, given Bob's performance, does he look normal? Okay? Or does he look somehow abnormal? Now, sometimes students are hesitant. I don't want to say if he's intoxicated or not. I don't want to say, right? Well, I sometimes then rephrase the question and I say, well, listen, here are the population parameters that we see normally. Here's what Bob did. And Bob was in a car accident last night, but he's okay, all right? Survived the car accident. It was pretty bad, but he didn't even go to the hospital. And what I want to ask you now, instead of saying, do you think Bob is intoxicated? I want to ask you this. Do you think Bob should maybe go to see the doctor? See, this becomes then sort of less judgmental and trying to like maybe help Bob out. What am I getting at here? Well, Bob is pretty slow. Remember, reaction time, just like running around the track kind of a thing. The higher your score, the slower you are, right? 258 milliseconds to hit the bar. Bob's taking 338 milliseconds to hit the bar. Slower. Higher scores in this case mean slower. Lower scores would mean faster, okay? Well, let's take a look. Let's take a look because this isn't just an opinion, right? I have some data upon which to make my assessment. So here's Bob out here at 338 milliseconds. And what I want to do is I want to convert that to a z-score. I know Bob is slower than the average person. I kind of want to know how much slower, right? In terms of standard deviations. I mean, if Bob was at 263, I'd be like, I'm not worried about that. That technically is not average, but there's a lot of people that are in here, 263, 270, 252, 247, right? I mean, there's lots of people in this area. And so on. I mean, the standard deviation is 37. But let's take a look at Bob. Bob is sort of way out there, right? What is Bob's z-score? Well, let's do this. 338 minus 258 divided by 37. And let's do that. 338 minus 258 equals, divided by 37. Bob's z-score is 2.16. Okay? Bob's, was that the same as we got on the other one? I just made up these numbers. Bob's z-score is 2.16. Wow, that's out there, man. More than 2 standard deviations away from the mean. If we convert that to a percentile, what we're going to see, 2.16, 98.46. That's the number of people that would score at or below Bob's score. And Bob would be only 1.54% of the people are slower than Bob. Wow, that's kind of, Bob has a very high percentile rank here. And in fact, so here's my thinking, and it's a logical conclusion to this. I don't expect everybody to be at 258. But Bob is like out there. Bob is really slow. This is not my opinion. More than 2 standard deviations away. So Bob doesn't look normal. Now, if someone gave me the option, do you think Bob's intoxicated or not intoxicated?
I would have to say intoxicated. By the way, I could be wrong. Whenever I'm making a guess, I could be wrong. Whenever I'm making a guess, I could be wrong. Okay? That's okay, but I'm going to make an educated guess, and that's what this is all about. Now, if you don't want to do the intoxication example, we could say, you know, Bob is so slow. He's in the 98.46 percentile. There's only a 1.54% of the people that are slower than Bob. I think Bob needs to go after his car accident. I think he needs to go and get tested by a doctor because he may have a closed head injury. All right? What I'm saying here is Bob is out there. He's an extreme deviation from the mean. Okay? Now, it could very well be, you guys, this is not, I'm basing these conjectures on the data. It could very well be that Bob was just not paying attention. And if we did this again, he would be at 260 or 247 or something like that. Okay? It doesn't mean that he's intoxicated. It doesn't mean that he has a closed head injury. It means that Bob is way out there. Okay? And so what I want to do now is talk about this logic based on these numbers and z-scores and percentiles. Here's the logic, okay? Let's talk about somebody new coming into the lab. We don't have any idea what they're about, okay? Let me ask you this question. And these are all questions to think about. Think this through. Think about it. I am absolutely non-apologetic about that as a college professor because I feel my job is to get people to think and use logic and rationale for making decisions, not to tell you what to think. That is absolutely not my goal, okay? I want you to think and use educated decision-making tools, but I'm not here to tell you what to think. So somebody new comes in. So let's say, Mary comes into the lab and sits down. Before we give Mary the reaction time test, what do you think is going to be her reaction time? Now, please don't say, I don't know, because that all you're saying to me is you're not thinking. What would be your guess for her reaction time? Where would you place your dollar if we were doing a bet here about what Mary's reaction time would be? Where would you place your dollar? Where would you place it? Now, some people would say, well, probably around 258. Okay, I think that's a reasonable response. If somebody said, well, I would put it at 350 milliseconds, I'd be like, 350 milliseconds out here? Without any other information, why would you think that Mary would be out here? I mean, that's a bad bet. Could Mary end up being out here? The answer is, hells yeah. She could end up being out here. I don't know what she's going to do. What I want to do is make a good bet, okay? If you go to a horse race and you see this nice slick horse with really nice small jockey on top with nice silks, and oh my God, it's just glistening and muscular. And if you saw another horse that was 40 pounds heavier with the jockey and the horse, I would say, which horse do you think is going to win the race? I'd go with the sleeker horse with the smaller jockey. It doesn't mean that one's going to win. That would be my guess. Everybody understand here? Okay? I'm not asking you to predict the future, and if you're wrong, you're done. I'm saying, what would be your guess here? What's the most likely outcome? And my guess for Mary would be right here, exactly at 258. Could I be wrong? Of course. Of course, of course, of course. Why did I say 258? Well, the mean ends up being the mode as well. That's the most frequent reaction time that we see. This is the most frequent reaction time that we see. If you're forcing me to guess a specific number, I would say 258. Now somebody might say, well, what about 265? Yeah, 265 is probably a pretty good bet, but 265 occurs less frequently than 258. What about 247? 247, I would say probably a good bet, but not as good as 258. You see what I'm doing? I'm going to hone right into that and say my single value guess would be 258. That's a tough bet, okay? If you said around 258, awesome, okay? If I forced you to give me a single number, an actual number, why wouldn't you say 258? That is the most common, the most frequent. Okay, everybody with me? It may be that Mary's going to be down here, or here, or here, or here, or here. I don't know. I'm betting. I'm betting. Listen, I like to play poker. And what I always tell people is that when you get to be a good poker player, you do a lot less gambling than you do betting. And sometimes people scratch, what are you talking about? I thought it was the same thing. Well, I have a different operational definition for betting and gambling. If I pick up my hand and I have a 7-2-1 suited, for those of you who don't know poker, that's a very bad beginning. And you should throw it away. And I do. Sometimes what happens is I threw away my 7 and 2, and then the dealer deals out 3 sevens. Oh my God, I would have had 4 of a kind. That's a huge, very powerful hand. And sometimes people say, I shouldn't have thrown that hand away. And I'm like, oh, no, no, no. You absolutely should throw the hand away. Making a good bet is different than doing the correct thing. That is, sometimes you throw away a bad hand and it ends up, oh my God, you should have had it. You shouldn't gamble like that. You make your bets on the most probable outcome. Okay, on the most probable outcome. I was in a poker tournament once, and I had a 98% chance of winning, and I was beaten by somebody that had a specific card. And so I was out of the tournament. I didn't beat myself up over it because I made the best bet. I'm going to ask you for the rest of the semester, make good bets. That's what I want you to do. Based on probabilities, I want you to make your best bet. Whether you're right or wrong ends up being, not that important because, just like my poker game, if I continually make the best bets that I can make in the long run, I'm going to win. Okay. Anyway, so this would be my bet for Mary. And in fact, even because I know what this means, I would say 258 plus or minus that 37 because that's the average amount that scores deviate from the mean, okay? And what I'm talking about here is this. This is what I expect to see from Mary, somewhere in here. This is what's probable. This is what's likely. This is what's normal. Okay? But at some point, this doesn't just go on and on. It's like, oh, anything's normal, anything's probable, anything's expected. No, that's crazy. Okay? That at some point, we're going to reach a point we're going to say, well, this is really not what I expect to see. Okay? I certainly didn't expect to see this if Bob was normal. Okay? Before I know anything about Mary, I'm expecting to see something in here. It's very logical. I hope that makes sense to you. Okay? So, at what point? There's a point. At some point, we're going to say,
This is in the area that is not expected, right?
And by the way, down here too, this is not expected. This is an improbable outcome for somebody who's normal. This is unlikely. We're unlikely to see this from Mary, right? And I'm going to say, you know what? This is weird, because that's one of my favorite words. And by the way, it's weird because the I doesn't come before the E. That's one of the things that makes that word weird. And I use it a lot, and I never want to misspell it. And so I had to come up with a way to remember it. I always remember it because I'm like, we are weird. We are weird. Okay? Anyway. Scientists, physicians, healthcare workers, educators, business folks, we need to define what's weird. Okay? What's unlikely? What's improbable? Okay? What are we expected? What's not expected? And this is a wild thing because a chemist in Brazil and a psychologist in Canada and a biologist in China and an occupational therapist in Australia. It's weird. The sciences and the medical profession have sort of agreed, for the most part, not 100%, but pretty damn close, have agreed that we're going to define this line here that defines probable from improbable, expected from unexpected, normal from weird. We're going to define that as what's in here is the middle 95%. And once we get beyond the middle 95%, we're going to say that's weird. Okay? Bob is outside of that middle 95%. Okay? Now, we've talked about this 95%. We said that it is 2 standard deviations is about 95%. Okay? We're going to get more exact with that. We're going to get more exact. It's good to think about the middle 95% as being about 2 standard deviations. But the 95% is actually defined by a z-score of minus 1.96 and plus 1.96. And I'm going to ask you to look at your z-score table, the unit normal table. What do we want here? If this is the middle 95%, then this would be 2.5% here and 2.5% here. Okay? Middle 95, 2.5, 2.5. If you look at the unit normal table for a tail, and remember 2.5% looks like this. Don't look at 25%. This is what 2.5% looks like in terms of proportion. So 2.0250 in the tail will give you a z-score of 1.96. Negative and positive. This z-score, not 2.00, but this z-score defines the middle 95%, or conversely defines the extreme 5%. Middle 95%, extreme 5% is given by this. Now, I'm still, this is about 2, right? For this class, we're going to be specific. It's 1.96, 1.96, and we're going to use that lots and lots. 1.96 is what we're going to use, okay? Next year, when you're out of stats class, if you're thinking to yourself, well, it's about 2 standard deviations, that's fine. That's a good way to think about it, but specifically it's 1.96. What's expected of Mary? What do we not expect to see? Now, if Mary ends up having a z-score of 2.7, I would say she's weird too. If she's got a z-score of 1.23, then I would say, okay, that's within the realm of what I expected. That's what I mean, and that's what you meant when you said, well, I expect her to be around 258. Around 258 means here. It's a pretty liberal kind of assessment, right? She can go as far out as 1.95, okay? That's 1.95 standard deviations. But at some point, we gotta, like, say, okay, enough's enough. She's weird. What you do with that weird, I mean, it could be that she's just, you know, didn't understand the directions. It could be that she's just the slowest person around. It could be that she's intoxicated. It could be that she has a closed head injury. It could be that her vision's bad. But the point is, if she has a z-score of 2.41, she's weird. I mean, based on this information. Okay? All right. So then we're going to make a huge step into using this to make an assessment about some research questions. Okay?